For decades, humanity has clung to a captivating narrative of the universe's origins. But what if that cherished tale, which we believed to be elegant and profoundly true, is fundamentally flawed? We were led to believe that following the Big Bang, a cataclysmic explosion that gave birth to everything, a profound, starless darkness enveloped the universe for hundreds of millions of years. Only after this epoch of silence were the first luminous stars expected to flicker into existence. The James Webb Space Telescope was meticulously crafted to penetrate this primordial veil and capture the ancient light emitted by the universe's earliest galaxies. However, when Webb turned its gaze back towards the dawn of time, it did not encounter mere flickers. Instead, it unveiled a dazzling firestorm of cosmic activity. It discovered celestial objects so inexplicably bright, astonishingly massive, and intricately complex that they defy all pre-existing models. These enigmatic lights pose a dramatic question. What are they, and from where do they originate? The revelations from Webb are compelling scientists across the globe to confront a startling realization. We may very well have misjudged the very story of the universe. To grasp the astonishment rippling through the astronomical community, it's essential to first consider the expectations that governed their inquiries. The entire framework of cosmic understanding rested on the standard model of cosmology. This model, a remarkable synthesis that has proven successful over decades, sketches a vivid and specific portrait of the universe's initial billion years. It commences with the Big Bang, roughly 13.8 billion years ago. In the first 380,000 years, the universe was an opaque, boiling cosmic soup, a tumultuous environment so hot that atoms couldn't coalesce. Only after cooling enough for protons and electrons to combine into the simplest elements, hydrogen and helium, did a pivotal moment known as recombination occur, rendering the universe transparent. Yet therein lay a dilemma. This newly clear cosmos held no stars, no sources of light. Thus began the cosmic dark ages, an endless, starless night dominated by drifting clouds of gas. According to the standard model, gravity began its slow, relentless work on this vast emptiness. Over millions of years, it coaxed gas into increasingly dense groupings. After an estimated 100 to 200 million years, the heart of these clumps reached such intense temperatures that nuclear fusion initiated. This marked the cosmic dawn. The first stars, dubbed Population 3 stars, were believed to be colossal giants, perhaps hundreds of times the mass of our Sun, living brief, tumultuous lives. In time, these stellar titans would cluster together, giving birth to the first small, chaotic proto-galaxies. What the Hubble Space Telescope had revealed in its explorations aligned with this theory. It showed galaxies from when the universe was still less than a billion years old, exhibiting the characteristics predicted by the model: small, disorganized, and faint. They were the cosmic toddlers of galactic formation. Thus, the timeline appeared well-defined: an extended dark age, followed by a slow dawn, culminating in a gradual accumulation of diminutive galaxies over vast stretches of time. This scenario was the definitive narrative that Webb was expected to validate. Then came the James Webb Space Telescope, transcending the capabilities of Hubble, a veritable time machine in its own right. Webb excels in the realm of infrared observation, a critical distinction that enables it to peer deeper into the cosmos. As the universe expands, the light emitted by the first galaxies has stretched and transformed, shifting from visible wavelengths into the infrared spectrum over the course of 13.5 billion years. Webb, with its breathtakingly expansive golden mirror, was designed to capture these elusive signals. Its mission was nothing short of monumental: to slice through the cosmic dark ages and illuminate the first flickers of infant galaxies. In 2022, after a remarkable journey, it opened its celestial eye to gaze into the unfathomable depths. Scientists anticipated the emergence of faint reddish smudges against the vast cosmic backdrop. The JWST Advanced Deep Extragalactic Survey, or JADES, was set to scrutinize a single patch of sky for hundreds of hours, crafting the most profound image of the early universe ever conceived. Confirming the entrenched narrative would have been a momentous victory for cosmology. Yet what Webb returned was not a mere confirmation. It was a cosmic bombshell that has recalibrated our understanding of the universe. When the first deep field data from the James Webb Space Telescope began to arrive, the scientific community was confronted with astonishing revelations. Instead of the faint, simple galaxies that had been anticipated, Webb unveiled a tapestry of glowing beacons, astonishingly bright, astonishingly massive, and far more developed than expected for their age. In early 2023, an astronomical team announced the identification of 6 candidate galaxies observed merely 500 to 700 million years after the Big Bang. Dubbed universe breakers, these galaxies exhibited masses comparable to the Milky Way's current population of stars. The analogy was striking. It was akin to encountering a newborn baby standing 6 feet tall, sporting a full beard. This revelation shattered established notions of cosmic development. Researcher Joel Leja articulated it well, stating the revelation that massive galaxy formation began extremely early in the history of the universe upends what many of us had thought was settled science. As discoveries piled up, astronomers identified MOM Z14, famously known as the mother of all early galaxies. This remarkable galaxy existed just 280 million years after the Big Bang, marking it as one of the most distant galaxies ever confirmed through spectroscopy. Another contender, JADES GSZ14-0, is estimated to have formed around 290 million years post-Big Bang. Contrary to expectations that a galaxy of such youth would be a chaotic cluster of a few nascent stars, these galaxies were found to be colossal and strikingly luminous, each housing star masses equivalent to hundreds of millions of suns. This raised an intriguing question. How could nature conjure such vast structures so rapidly? The continuing theme underscored a striking reality. The early universe wasn't a tranquil nursery, but rather a bustling factory, rapidly assembling grand and complex galaxies at a pace that challenges the parameters outlined by the standard model of cosmology. The cosmos appeared to hit the ground running, with these bright, nascent galaxies posing profound paradoxes that challenge our fundamental understanding of cosmic evolution. So, does this mean we were wrong about the origins of these galaxies? The standard model of cosmology relies heavily on a crucial component, dark matter. This theory postulates that unseen halos of dark matter collapsed first, providing scaffolding into which normal baryonic matter was drawn to form galaxies. However, this process is limited by the rate at which gas can cool and convert into stars. The universe breaker galaxies seem to have transformed almost all of their available gas into stars with alarming efficiency, a scenario current models struggle to accommodate. This suggests several unsettling possibilities. First, our comprehension of star formation may need reevaluation. It's conceivable that the first generations of stars formed with unprecedented efficiency, which would necessitate major revisions to core principles of astrophysics. Second, perhaps the cosmological model itself is incomplete. The discovery of these massive galaxies at such an early stage fundamentally challenges pivotal aspects of our galaxy formation theories. While the overarching framework of cosmology maintains its robustness, these anomalous findings indicate a need for significant amendments. Beyond mere size, the chemistry of these galaxies is equally perplexing. In the realm of astronomy, any element heavier than hydrogen and helium is classified as a metal, and these elements are exclusively produced within stars. Typically, it takes an entire generation of stars to live, die, and enrich the interstellar medium with these heavier elements. Nonetheless, Webb has unveiled substantial amounts of oxygen within galaxies like JADES GSZ14-0, which formed just under 300 million years after the Big Bang. For such a galaxy to contain that level of oxygen, it would need to have undergone at least one complete cycle of stellar birth and death, suggesting that the cosmic dark ages were compressed into an extraordinarily brief time span. Conversely, Webb is also transforming our understanding of the epoch of reionization, the pivotal event wherein the light of the universe's first objects penetrated the opaque fog of primordial hydrogen. Data from Webb indicates that the principal agents of this monumental process were not merely a handful of massive galaxies, but rather vast assemblages of tiny dwarf galaxies. This leads to an intriguing conundrum. While the universe was populated with innumerable small galaxies performing the cleanup tasks, there also existed a surprising number of universe-breaker galaxies that expanded too swiftly. This contradiction has left theorists racing to reconcile these conflicting observations, further deepening the mysteries of the early universe. What we're witnessing is not merely a development in astronomy, it's a potential paradigm shift in our understanding of the universe. The James Webb Space Telescope, JWST, was designed to trace the origins of cosmic structures, specifically to explore the first galaxies and stars. However, its findings are reshaping our fundamental narrative about cosmic evolution, indicating that the preface to our understanding of the universe needs a substantial rewrite. The discovery of galaxies like MOM Z14, which emerged startlingly early on, coupled with the existence of so-called universe breakers, suggests that galaxy formation did not follow the slow bottom-up process that many cosmologists had long envisioned. Instead, evidence points to the possibility that the universe possessed the capability to create large, mature structures almost from the very beginning, just several 100 million years after the Big Bang. This challenges our previous assumptions and compels us to reevaluate our models of cosmic evolution. For scientists, this emerging scenario is not a crisis. Rather, it represents an incredible opportunity brimming with potential. It indicates that there is new physics waiting to be uncovered. The standard model of cosmology, which has served as a cornerstone of our understanding, is now evidently incomplete. These seemingly impossible galaxies are vital clues that could lead us towards a more accurate and comprehensive theory of the cosmos. We've transitioned from merely wondering whether galaxies existed 300 million years after the Big Bang to meticulously analyzing their chemical compositions, revealing insights into their age, formation, and the processes that led to their creation. This leap in understanding is truly astounding, and it suggests that our textbooks are being rewritten in real time with each new data release from JWST. The narrative of the universe is increasingly fluid rather than static. The James Webb Space Telescope hasn't just opened a new observational window, it has illuminated the fact that the structure of the metaphorical house we thought we understood is fundamentally different. Instead of faint cosmic embers, the first objects JWST detected turned out to be cosmic lighthouses, illuminating the vast gaps in our knowledge and urging us to rethink what we know about cosmic history. In conclusion, if you've enjoyed this exploration of groundbreaking celestial discoveries, don't forget to share your thoughts in the comments. Are we mistaken about the timeline of the universe, or is our understanding of the formation of the first galaxies fundamentally flawed? Be sure to subscribe and hit the notification bell as we continue this extraordinary journey into the final frontier together.